Welcome back, everyone. This lecture here is intended to be a kind of supplement to the last. In the last lecture, we were talking about the famous square of opposition of Aristotelian logic. We talked about four different kinds of categorical claim, A, E, I, and O. And then we talked about the relationships that govern that square, the different rules that correspond to the relationships that relate each of the types of claim. By the way, the claims may seem rather limited or limiting in terms of which sorts of claims we can actually express with them. But in fact, if we're creative, we can actually present lots of ordinary declarations or assertoric sentences in terms of these four types of categorical claim. So, for example, even a claim like, let's say, Socrates is a man. If you think about that claim, it obviously doesn't seem to fit one of our four patterns. For one thing, it uses this individual term Socrates rather than any categories. Now, man, we could more or less easily convert to men. But how are we going to take care of this particular term, this individual term, Socrates? Well, one thing we might do is use a kind of artifice here. We might say, well, consider this category, things identical with Socrates. Now, that's a generic term. Of course, it's only going to be true of Socrates. It's only going to apply correctly to Socrates. It's a category that holds of only one thing. But nevertheless, it's the sort of term we're looking for. And so if we then construct the claim, all things identical with Socrates are men, then we seem to be capturing the spirit of the original claim as well as putting it in the form that we would like it to have, namely in this case an A claim. And so if we're creative like that, we can often fit the lots of ordinary declarations into one of these four forms. Okay, so the goal I want to talk about today, the goal is to think about how to use the rules that we just learned in a proof. If you go on and study more logic or more mathematics, then this is sort of at the heart of the type of work you'll be doing. When you go on and study more math or study more logic, you can construct a lot of proofs. And proofs proceed formally. They proceed according to rules, just like the rules that we've learned about how to move from one categorical claim to another. So here's a simple example. Suppose we start with a particular categorical claim as a premise, like it's false that all rectangles are non-squares. Okay? Certainly a bit awkward English, but maybe that's exactly the point of proceeding to try to develop it, to transform it into a more coherent, a more easily comprehensible type of claim. And in fact, we may be told that we can derive the following conclusion from that premise: some rectangles are squares. And so the question before us is, how can we construct that proof? How can we illustrate how to arrive at this conclusion from this premise by using the rules that we've learned in the previous lesson? We might note first that we start with the negation of an A claim. All rectangles are non-squares is an A claim, and it's negated. We've got an it's false that in front of it. And we need to move to an I claim somehow. Some rectangles are squares is an I claim. If we think about the relationship between A and I, we might think of the subalternation rule. And subalternation does indeed relate those two types of claim. But of course, it relates them only if they correspond, right, in our technical sense of having the same subject and predicate. These claims here, of course, do not correspond because the premise the premise's predicate is non-squares, while the conclusion's predicate is squares. So we can't just use subalternation immediately. The use of the non prefix obviously makes us think of complements, and so that should get us thinking about the relations that we learned about that are not depicted on the square, namely conversion, obversion, and contraposition. And in fact, probably we want to think about obversion because we need somehow to be able to transform non-squares into squares, but we want to keep rectangles the way it is. We don't want to bring in non-rectangles. And notice that if we were to apply contraposition, contraposition converts both categories to their complements. So we probably don't want to apply that because we'll end up with non-rectangles. So let's try obversion. Okay? The rule of obversion, or the rule of obverses, if we apply it to this premise here, it's false that all rectangles are non-squares. Well, we'll leave the it's false that bit alone out front. Now we have an A claim here, and so to construct the obverse of that, we're going to slide horizontally along the square to get an E claim. So that's no rectangles or squares. And then we need to, sorry, no rectangles are non-squares, but we need then to replace the predicate with its complement term, and that's, of course, squares. So the obverse, if we apply the rule of obversion to our premise, we end up with this claim. It's false that no rectangles are squares. Okay. Notice in constructing this, we replace non-squares with squares, as according to the rule of the obverse. Also, we move from an A claim to an E claim, again, just by the nature of how obversion works. And it's false that we just leave outside, and we're totally safe doing that because we know that the claim that follows the it's false that in our intermediate conclusion here, no rectangles or squares, we know that that's exactly equivalent to the claim that all rectangles are non-squares. We know that because all categorical claims are equivalent to their obverses. Okay, great. So now we've reached this claim. It's false that no rectangles are squares. We still have in mind to try to prove this conclusion, some rectangles are squares. And if you just reflect for a moment, you can probably see that the rule of contradiction now can apply immediately to this. We have in our intermediate conclusion the negation of an E claim. Our ultimate conclusion is an I claim. And this time, our claims correspond. They have the very same subject term, the very same predicate term. And the rule of contradiction says if we know that some E claim is false, well, then it must be the case that the corresponding I claim is true. Okay? And the ultimate conclusion toward which we're angling just is that corresponding I claim. And so if we apply the rule of contradiction to our intermediate conclusion, we get exactly the thing we were looking for. Some rectangles are squares. Again, notice a few things in deriving this conclusion from this intermediate step. Obviously, we're moving from an E claim to an I claim. That's how the rule of contradiction works. And again, since the E claim is false, the I claim must be true. And finally, note that we're done. Right? This was the conclusion that we're trying to reach. We've matched it exactly, and so we can stop. We just kind of tried out a few rules here and saw what came out of them. That can often be a good strategy for attacking these things. As you try more of them, you will get a feel for which rules are likely to help you in a particular path to a particular conclusion. But if you ever get stuck, well, just try something. Just try applying some rules and see how it goes. We are limited by the number of rules that we have. That's in a way a bad thing, obviously, because that means that we're being very strict about which sorts of claims we can write down given some starting claim. But on the other hand, what's good about that is that, well, there's only a few things to try. If we feel like we're stuck, we can just try something, and maybe that will Maybe that will sort of inspire us to find how to reach the conclusion. Finally, I just want to talk for a minute about symbolic logic. In effect, we're doing this already. You can imagine that we define the following sort of shortcuts, the following sort of abbreviations for what we've been doing. Suppose we write all SRP simply as capital ASP, and some SRP simply as capital ISP, and so on for E and O claims. And for complements, we might just draw a bar over the top of the relevant category term. So if squares is represented by S, then we could represent non-squares by S with a bar over top. And to accommodate the it's false that prefix that we've already seen, we might just prefix a capital F to the claim. And so right now, looking back at our derivation, we might symbolize it just like this, by these means of abbreviation. We start with the claim that it's false that all R are S bar, that is, false that all rectangles are non-squares, false that all rectangles are non-squares. We then use the rule of aversion to reach the claim that it's false that no rectangles are squares. That was our intermediate conclusion here. And then finally, we applied the rule of contradiction to reach this claim: some rectangles are squares. Okay, and of course, that was the thing we were trying to prove. This kind of symbolization, this kind of abbreviation, highlights this point about validity that we've seen before, namely that validity is, at least in the main, a matter of formality, of formalism, of applying inferences according to formal rules. And what's nice about that is that a computer, for example, could be trained to generate such inferences as long as it has internalized the rules that we've learned. Right? If you could program a computer to say, well, whenever you've got a claim like FERS, you can write down this claim, IRS, and so on for all the different possibilities sanctioned by our rules, then the computer would be able to generate inferences just as well as any of us, and in fact, much more quickly. Now, the sort of very powerful idea here is that the computer can do this without any understanding of what these symbols actually mean, at least intuitively. You might sort of argue that the meaning is contained in the rules and that there's nothing else to the meaning of these symbols, but intuitively the computer doesn't have any understanding of these symbols. The computer is merely manipulating them according to some preset rules. And of course, that's what computation is, right? That's what modern computers do. They are masters at manipulating symbols. And the meaning of the symbols, or how we might want to interpret them as human beings, really doesn't factor into what the computer is doing at all. The computer has internalized some rules. The computer knows that when certain words are put together, it's to execute certain commands. But it doesn't really know what it's doing, right? It's just very good at following instructions. And that's what these proofs are. They're exercises in following instructions. If you think about the nature of logic, this is obviously not a class in the philosophy of logic, but naturally, if you go on to study logic, you might start to ask, well, what are we really doing here? What is logic about? What does it mean? What is it? And many philosophers of logic have had the idea that a logical system should depend only on strict formal rules of just this kind. Right? We want logic to depend on these formal manipulations, formal syntactical rules that we can specify precisely. Right? This is why we're being very strict about how to use these rules. There is a sense in which it's false that all rectangles are non-squares and some rectangles are squares aren't meaningfully different from each other, right? They literally say the very same thing in a certain sense. But they are formally different And we can show that using formal syntactical rules of manipulation, we can go from one to the other. And it's that idea that's important now. So we're sort of abstracting away from meaning, and we're reaching something that's defined only in terms of symbols. And the idea that these philosophers have had is that if, by contrast, logic depended on vague notions of meaning that might even be subjective, then it wouldn't have the kind of certainty or power or universality that we want to demand of logic. Logic is supposed to capture something necessary about the world or necessary about thought, or in some way captures something to do with laws of reasoning. And the idea has often been that logic would be unsuitable to do that unless it rests upon these kinds of rules that are unassailable and unambiguous and unvague. There shouldn't be any doubt at all about how the rules apply. We're not going to have questions underlying our logic about, well, what does or actually mean, or what does and actually mean, or what does all actually mean? We want nothing unclear about what those words mean, and we're in effect going to cash out that meaning strictly in terms of these formal rules of symbol manipulation. And so it doesn't matter what your home language is, if you are versed in a logic of this Aristotelian kind or of many other kinds, then you have a common language to speak, you have a common place to start from, and there's no sort of ambiguity about how to speak, as it were. There's no ambiguity about how to move from one claim to another. This is why logic and mathematics get so formal. If you go on to study it, this is all you do after a while, right? Mathematics is in many ways the manipulation of symbols, just like computing, and logic is too. And that's why you have to construct proofs in geometry class, right? Your geometry teacher was gearing you up for this idea of formalism, this idea that the sort of powerful idea of math is that you can prove things only using manipulations of symbols. You hardly have to know what you're talking about, as long as you're really good at following instructions. Now, of course, in practice, coming up with difficult proofs of theorems in mathematics does require some ingenuity, it does require some creativity. And that has largely to do with the fact that mathematicians aren't thinking about the sort of most basic laws of inference. They're thinking at a higher level. But the goal often for a philosopher of mathematics or a philosopher of logic is to be able to spell out any rule of inference that any mathematician or logician ever uses in terms of symbol manipulations. And so this is one area where philosophy of mathematics really becomes an interesting enterprise, because you start asking things like, well, what is it that really allows us to move from the claim that, maybe I've got a point and a line with a point not on that line. What is it that allows us to say that there's exactly one line through that point that's parallel to the given line? Can we encode that reasoning formally? And of course, famously, that sort of reasoning depends on a kind of Euclidean or flat interpretation of geometry. And there have been other geometries that say, well, actually, maybe there are multiple lines that go through that point that are parallel to the given line. Or maybe there aren't any lines at all that go through that point that are parallel to the given line. Right? And so you have this kind of effort of trying to shore up our intuitive mathematical notions with logical rigor, with notions that obey formal rules about which there is no ambiguity or dependence on intuition or other vague things that mathematicians intuitively need to use in their work. So, if this kind of manipulation of symbols is interesting to you, do consider signing up for Philosophy 120. That's our Introduction to Logic course. Or for that matter, think about courses in mathematics or in computer science. Okay, that's it for our formal stuff. Our last lecture, or perhaps set of lectures, will be about applying critical reasoning to particular cases. So I'll see you next time for that.